Hello guys, today I'm going with this video to explain to you a very exciting phenomenon which happens by light. It is called the photoelectric effect. Now, light so far is shown to have a wave aspect of light, which means that the energy of light moves through space as waves, and it means that the energy of light depends mainly on the amplitude of this wave and thus on its intensity. So as the amplitude of the light wave increases, the wave theory says that its energy increases too. Now, is this true? We saw that in the late of 1800s many experiments were done, and they show that light cannot be transformed, or the energy of light cannot be transformed as waves. It cannot be, and it does not depend on the amplitude of this wave. One of these important experiments is the photoelectric effect. This applet can help us to understand this phenomena. We have here a certain closed tube, let me say, and here I have a piece of metal. Here we have a light source where we can vary the frequency and the intensity, and here we have a battery which is connected to this tube. Now there is an important point you have to know it about the metals. All metals in reality have something called free electrons on their surfaces. This is a surface of metal. Then there are a lot of free electrons that are responsible for the conductivity of the metal. Why does a metal conduct electricity? Because it has free electrons, which means that they are not bound to any atom. They are not circulating around any nucleus, let me say. And simply you can extract these electrons from the surface of metal if you give them enough energy. If you give them enough energy, then they are ejected in space. And I think we all see this phenomena by simply using a hammer on the surface of a metal. What do we see? We can see sparks. The sparks means that electrons are ejected in the free space, so we are extracting electrons from the surface of this metal. And now we want to extract these electrons, but not using a hammer. We want to use light. Does light extract electrons? Maybe yes and maybe no, because light has energy. Since it has energy, then it can or cannot extract electrons. It can if its energy is enough, and if not, then electrons will not be extracted. Now I'm assuming that light moves in space as waves, which means that the intensity of the light wave is the only character that affects the energy of light. And so if I vary the intensity, I should gain more electrons in the space, and if I vary the frequency, then there must the number of electrons will remain the same, because as I said before, the energy of Light wave does not depend on the frequency of the wave. Now, what do I have here in this experiment? This metal is sodium, as you see, and the light is using now red of lambda 778 nanometers with zero intensity. Now I will increase the intensity of light. This is 30, 40, 50, 60, 70, 80, etc. until 100, and no electrons are extracted from the surface of metal, knowing that there is no voltage here, which means that if electrons are extracted, they must reach this area here. So, as you see, when I use red radiations with a very high intensity, there is no electrons extracted from the surface of this metal. But the surprise is if I increase the frequency of light from red, here red, into yellow, orange, then yellow, this is yellow, and also no electrons are extracted, I will increase more and more to green. Oh, at green, electrons are observed to leave the surface of metal. This means that the energy of light depends on the frequency of the used radiation. Another surprising result is that if I use this radiation, green radiation, with, let me say, this intensity, so of course I expect less electrons to be extracted, and this is true. But the main question is that what's about the energy of each electron, or energy per electron extracted from this plate to here? Is it the same if I increase the intensity of light? Does each electron carry more and more energy or not? This is a main question, because wave theory expects that when the intensity of light increases, then the electron will be extracted with more energy, So this is what does the wave theory state. Now, to test this if it is true or not, we will use this battery in order to apply a voltage between these 2 points, a potential difference in the negative direction. Let me put minus 0.2 volts. What is meant by minus 0.2 volts? Here, if you see, there is minus, and here you have plus. So, when the electron is extracted and wants to move, it has kinetic energy at this point. It moves, but there is an opposition because this is now minus. So, there is an opposition which lets it not to reach this point. As you see, the electrons reach only this point and then go back. This looks like what? If you eject a certain object from your hand up, then depending on the initial kinetic energy, it can cover a certain distance and then come back, because your kinetic energy at the initial point is enough to let the object move a certain distance. And now, because electrons are ejected with a certain kinetic energy, this kinetic energy is enough to let each electron to reach this point. Now, if I increase the intensity, what does the wave theory state? It states that the electron must move more, because if I increase the intensity, then each electron must carry more energy. More energy means that it must cover a more distance. Let me see what happens if I increase the intensity. Then we observe that more electrons are extracted because more light is falling on the metal, but they cannot move more, which means that if they reach the same point with less intensity or more intensity, if they reach the same point, this means that the same energy, or sorry, the same initial energy is carried by each electron in all cases. Let me see. This at 22% of intensity, each electron reaches this point, okay? And then with more intensity, we observe that also the electrons reach this point, but more and more electrons are extracted from the metal, but not with more energy, but with larger number of electrons are extracted. Now, how to explain this important phenomena? It is very simple. A very important scientist called Max Planck. He is a German scientist who studied this phenomena very well, and he concluded that the energy that light can give to an electron is quantized, which means that which means light can give an electron a multiple of a unit quantity of energy, or let me say a unit of quantity of energy. Unit quantity of energy, which means that the least quantity of energy, or in other words, light can give for a certain object, for the electrons, a quantity, multiple quantity of energy. Here, let me write this unit quantity is given by Planck. E1 equals h in u, where in u is the frequency of the used radiation and h is called Planck's constant, such that h is equal to this value. So light can give a multiple of this quantity, and cannot give 1/2 of this quantity or a ratio of this quantity. So when light arrives to an electron, it gives it one quantity of this or more quantities of this if it can give. Now, after a certain time, Albert Einstein came to say, in reality, we can say the radiation of light is composed of particles. Each one carries a quantity of energy that found by Planck before, which is equal to h in u. So this particle of light is called photon by Einstein. And now we stop to think about light as a wave, and it does not have in this experiment a wave aspect of light, but it has a particle aspect of light. Now, how to understand this on the photoelectric effect? So, what did Einstein mean, or Planck, is that when the radiation of light came with small frequency, which means that each particle of light reaching the plate, let me stop this, each particle of light, which is a photon, reaching the plate, it has an energy equal to h in u. But nu is small for red, and you must know that red has the least frequency between the visible radiations. So each photon coming to the plate has an energy equal to h times the frequency of red, which is very small. So when the photon reaches the plate and there is an electron on the surface which is bounded to the surface by a very small quantity of energy in reality, but the energy of the photon is less than this quantity of energy that bounds the electron to the surface, then this photon cannot extract the electron because the electron is bounded to the surface by more energy than that is given by the photon. But if I increase the intensity of light in the green area, what happens? I increase the energy of each photon coming to the plate. So the energy of a photon now is enough, which is more than the energy that bounds the electron to the surface. So if it is more than the energy bounding the electron to the surface, it can extract it, and the remaining quantity of energy becomes kinetic energy. So let me say that the energy bounding the electron to the surface is called W1, or W simply, and the energy carried by the photon is E. Since E is greater than W, then E will be equal to W plus the remaining, which is EK, kinetic energy. And to explain the other experiment, when there is a potential difference in the opposite direction, it is very important to explain this point. When I have a small intensity of light, but although I have small intensity of light, but each photon carries the same energy, h nu, where nu is the frequency of green. Now, each photon falling on the surface of metal carries an energy E equals h nu. This energy is enough to extract an electron, so electrons are extracted. Now, if I increase the intensity, this means that I increase the number of photons sent by the lamp, not increasing the energy of each photon. I am increasing the energy, the number of photons, and not the energy of each photon. So, as I increase the number of photons coming on the surface, more electrons are extracted from the surface because more photons are falling on the surface of the metal. So, we can write here E, which is the energy of a photon. Let me write here is equal to h nu is equal, this energy is equal to W0, which we will call work function, plus the remaining, which is EK of the electron. So W0 is called work function, or the energy that bounds of the metal. And it is very important to know that it characterizes the metal. It is a characteristic for the metal. Each metal has its own work function. And now you have to know that EK is the maximum kinetic energy of the electron, What do I mean by the word maximum? The surface of metal, let me imagine it as the metal as a vertical metal, like this. So I have free electrons on the surface and below, When radiations fall on the surface of metal, not all electrons are extracted with the same kinetic energy. The surface metals, surface electrons, will be extracted with maximum kinetic energy. The electrons below will be extracted with less kinetic energy. So this formula helps us to calculate the maximum kinetic energy, or the kinetic energy of the most speed electrons. So I can give you an example. If you go to close to a pool of water and you throw a stone on it, what will you observe? You will observe drops of water move up, but not all drops of water will reach the same maximum height. Some of them will reach a certain maximum height, others will reach a height less than the maximum one. Why? Because the drops of water that reach the maximum height, they were on the surface of water, but the other drops that were below them, they will reach a less height. So this formula helps us to calculate W0, which is the work function or the energy that bounds the highest electrons, and this is their kinetic energy. As you will see from here, not all metals have the same work function. I will choose zinc, then you will see that no electrons are extracted because W0 of zinc is much higher than that of sodium. So no electrons are extracted. And now I should go to the ultraviolet radiations in order to get again extracted electrons. Now, how to calculate W0 of zinc? It is very interesting way. As you see here, if I use 0 volts, then a lot of electrons can reach this point, which means that a current is circulating in the circuit, which is 0.47. But what if I write here minus 2 volts? Minus 2 volts, then the generator is opposite to the motion of the electrons, but there is still a very, very low current here, which means that a very number of electrons that can reach this one. But if I increase this by a little value, minus 2.1 volts, what happens now? Then the current is 0, which means that the highest electrons, as you see, highest energy electrons cannot reach this point, which means that the kinetic energy carried by each electron at this point is enough to let it to reach here and not to be in touch with this plate. So this means that the kinetic energy of the electron is equal to the electric energy that is opposite to it. And now I can write here, in this case, for zinc, the kinetic energy carried by each electron is equal to the electric energy opposite to the electron. In other words, this energy is equal to E times the voltage, the charge of the electron multiplied by the voltage. And in this case, I can calculate EK. So here, EK is equal to 1.6 10 negative 19 multiplied by the voltage, which is shown in the applet, which is 2.1 volts. And now this is equal to 3.36 times 10 to the power negative 19 joules. So this is EK, but as we know that H nu is equal to W0, which is unknown, plus EK. Which means that W0 is equal to H nu 6.626 times 10 to the power negative 34 multiplied by the frequency of the used, or multiplied by C 3 to the power times 10 to the power 8 divided by the wavelength 281 nanometer times 10 negative 9. This is the energy of each photon, which is 7.07 times 10 negative 19 minus this number 3.36 times 10 to the power 19, which is equal to 3.71 times 10 negative 19 joules. And if I divide it by 1.6 times 10 negative 19, it will be 2.32 eV in electron volts. This is how to calculate the work function of a certain metal. Another point to explain is what is called the threshold wavelength. Threshold wavelength means that it is the radiation with the maximum wavelength that let electrons to be extracted. And also we have threshold frequency. It is the radiation with the least frequency that is capable of extracting electrons from the surface of the metal. Let me see here what happens. The ultraviolet can extract electrons from the surface, but if I decrease, then the number of electrons becomes less and less. At this frequency, let me say 400 nanometers, as you see, less and less electrons are extracted. And now at 530 nanometers, no more electrons are extracted, or let me say at 540 nanometers. So I can say the threshold frequency of zinc, the threshold wavelength of zinc is 540 nanometers. This is the threshold wavelength. What does it mean? At this wavelength, the kinetic energy of electrons becomes zero. Thus, if I use this formula, then this one is 0 and this one is h, we will call it nu 0. So h nu 0 is equal to w0. Also I can calculate w0 from here. Also this formula is true because in u0 the frequency is equal to speed over wavelength, then hc over lambda 0 is equal to w0. This is why we say that the threshold frequency is the least frequency capable to extract, and lambda 0 is the maximum wavelength capable to extract, because they are inversely proportional. So we can conclude that a radiation of light of a frequency nu has a quantity of energy E total equals the number of photons carried by this radiation multiplied by h nu. What is h nu? Is the energy of each photon. So the total energy of a radiation reaching any point is n, the number of photons multiplied by the energy of each photon. This contradicts the wave nature of light. It does not depend anymore on the amplitude but on the frequency of the radiation, and thus this experiment shows that a new aspect of light called corpuscular aspect of light, the energy of light moves from one point to another as particles and not as waves. And now diffraction and interference show the wave aspect of light, but photoelectric effect shows the corpuscular aspect of light. Which one is true? In reality both are true, but how to differentiate between them? It is very, very simple. You can say that when light does not interact with matter, like in the case of diffraction and interference, then it behaves as waves. But when it interacts with matter, like when my body absorbs light, so there is an interaction. So this means that light behaves as particles and not as waves. Thank you and wish to meet you in more videos.